All right, so we're ready today for part two of our discussion about chapter one. And where we left off was we were looking at several types of functions that we may encounter in Calc 1 and down the road in other more advanced classes. So now we're going to take a look at the square root function. And of course, with the square root, you can't take a square root of a negative number and still have a real number. So the square root function is restricted to the first quadrant. We can't substitute any negative values into it, and no negative values can come out of it. So the range and the domain, we could write them as in the following way. So for the square root function, the domain is all non-negative numbers. And if you notice, the way the interval is written, we have the square bracket on the left, which means 0 is included in the domain, because you can substitute 0 into the square root function without causing any problems. On the right-hand side, though, with infinity, we always use the open or the round parenthesis. We do not want to indicate that we're including infinity. By convention, we always use the round parenthesis. So this is the one that we referred to yesterday as either semi-closed or semi-open. Yeah, I guess you can call it either one. The range is the same thing, because if you take the square root of 0, you'll get 0. If you take the square root of any positive number, you'll get a positive number. So the range and the domain are both everything from 0 up to infinity, including 0. Also, if you notice this description, non-negative. Non-negative means positive or 0. Okay, and of course, similarly, non-positive means anything that's either negative or 0. Okay, so we have to be careful with our terminology here. And anyway, this is what it looks like. If you notice, it's increasing at a progressively decreasing rate. In other words, doubling x does not double the square root of x. Just as a quick example, if I were to start with 4, the square root of 8 rather, sorry. The square root of 8 is approximately 2.83, which is clearly not twice as much as the square root of 4. So what that means is, as we move along the horizontal axis, as x increases, y is increasing, but not as quickly. So we have a function that looks something like this. We say that it is increasing at a decreasing rate. Okay, now the cube root function is kind of interesting because we can take the cube root of a negative number. So what that means then is that there's no restrictions on either the domain or the range. Okay, in other words, every real number can be substituted into this function, and every real number can be the cube root of another real number. So when you look at this graph, you see what I mean. The curve goes up forever, as you can see, and so the entire real number line is the range and the domain. So we can write that as the domain is the entire real number line, as is the range. It also has a very unique shape to it. If you notice, it's increasing at a progressively slowing rate. Then when it hits 0, it takes off again, but then it starts to slow down. It's a very strange function, but it kind of looks like an S flipped around. But this is what a cube root function often looks like. Okay, now, how do you find the domain of a function? I mean, clearly, what we're looking for is all the values of x that may be used in this function. Basically, what we're trying to do is avoid any values of x that can lead to either one of two things, division by 0, or a negative square root, or other negative root. So in other words, the domain basically includes all values of x that do not lead to division by 0 or an imaginary number. That's really what we're aiming for. Okay, so for example, for the function square root of x, well, we've just seen clearly we cannot include any negative numbers. Okay, so the domain, as we just saw a minute ago, is everything from 0 up to infinity, including the 0. For something like this, as we saw a little while back, we cannot allow division by 0. So the domain is basically everything else. Now, there's a couple of ways you can write this. But a common way of doing this is to write the numbers in the domain as an interval. And because there are actually two discrete sections of this interval, we're going to write it with set notation. Actually, let me just correct one little thing here. Okay, in other words, this U is the union symbol. You remember that from set theory. And it means you're combining two other sets into one big new set. So something like this means if you're looking at the real number line, you're basically including everything except 0 itself. So in other words, this interval is everything from negative infinity up to, but not including 0. And this is everything not starting at 0, but everything above 0 up to infinity. So in other words, you're covering the entire real number line except for the 0. So you've got two different infinite sets that are being combined in a union into the domain, which means you've got the entire real number line except for 0. Now, some of the other functions, it's not always extremely obvious what the domain and the range are. Sometimes it can get very tricky. But again, remember with the domain, we're trying to avoid division by 0 and any numbers that would cause an imaginary number. Like, for example, let's say we're looking at the fourth root of x. The domain is the same as it would be for the square root of x, because we may not take the fourth root of a negative number. And in fact, we can sort of generalize this a little. I just want to point out that the square root, fourth root, the sixth root are all referred to as even roots. Cube roots, fifth roots, seventh roots, these are all known as odd roots. And the key here is that you can take an odd root of a negative number, but not an even root. So on the even root side, we have to avoid any values of x that are negative. So for all of these, the domain is the same. Over here, the domain is the entire real number line. Okay, so that's the general result here. Even roots, we can only have a domain from 0 up to infinity, including the 0. Odd roots, the entire real number line is part of that. Okay, so basically what you're going to do when you're looking for a domain is look at all the input values and leave out the ones that would cause problems. Now, sometimes there's a large number of values that could cause issues. Sometimes the entire real number line qualifies as the domain of a function. So like for something like this, now often, by the way, the graph can be a very big help. If you look at your graph and you see that there are asymptotes, well, then clearly those represent holes in the domain. We saw one of those yesterday. For this one, y equals 1 over x, the domain is everything except 0. And you can see why, because the vertical axis is clearly an asymptote. For something like this, you can see just by looking at it, the domain is all the real numbers. Now, because if you notice, the curve continues to expand and will eventually cover the entire real number line. Now, the range is a very different matter, though. If you notice, the range, I guess I haven't really drawn this as well as I might have. This is the minimum value for the entire function. And so what that tells us is that the range is everything from -5 up to infinity. In other words, the way the graph is drawn, y can never fall below -5. There's no value of x. It could cause this to happen because x squared is always positive. It's never going to be the case that this x squared can be less than 0. And so therefore, y can never be less than -5. And that therefore represents the lower boundary of the range. Okay, so the range, remember, is the possible values of y. And usually the range is the trickier one to calculate. The domain is usually more straightforward, I think. But some of these, finding the ranges can be extremely challenging. All right. Now, this one we've already seen. We're very comfortable with this one. We know that the only potential value of x that could cause problems is 0. And yes, here's Symbolab's version of this. A very nice graph, I must say. But if you notice, too, although the question, the slide didn't really ask for this, it should be clear just by looking at the graph that the range does not include 0 either. And that's not going to be super obvious unless you look at the graph. Now, here's why. If you look at this carefully, no matter what value you substitute in for x, it's not going to be possible for this to equal 0. Okay, as long as 1 is in that numerator, there's no value of x that can make this equal to 0. And so that's why this is happening. Oh, we can get small, but it's never going to get to 0. All right. Now here's a tricky one. Now, superficially, it looks very straightforward. It should be obvious by looking at it that the domain cannot include +5. So we're going to use our same interval notation. We have the two sets from -infinity up to 5, not including the 5, 5 up to infinity, not including the 5, because 5 would cause division by 0. The range is a little trickier because it may not be clear that there's no value of x that can cause this function to equal 5. Okay, so by looking at the graph, you can see that there's asymptotes, the horizontal asymptote, and the vertical asymptote is 5. Now, we can prove this later on. We'll see how to prove this, but one thing you can also do is go to Symbolab. And I got it open here. Not just ask it to show the graph. Oh, I wasn't expecting that. Look at that. It's got the entire periodic table of the elements in there. I had no idea. Look at that. It's got some of these wacky man-made ones too down here, like UUP and UUS, and oh my God. They didn't have those when I was in high school. Now, the only unfortunate thing is they've actually changed this interface since the spring semester. So now I'm starting not to remember how to use it. I mean, I knew how to use it in the spring, and now all of a sudden they decided to play games here, and it's different. Oh my God. This is not good for me. Oh, thank God. All right. I guess I was supposed to call for the basic menu. This is the one that I'm used to seeing. I know it has all this other wonderful stuff, but I haven't had time to really explore it. You can feel free to play with it all you want because it is free. Y equals X, the ratio of X plus 5 over X minus 5. So when you're asking it, first you have to say go. Then you can say, listen, show me the graph. But now here it's not using the interval notation. That's strange. It used to in the spring. Yeah, they've really changed it a lot. All right, let's try this. Here's the domain. Everything except 5. Ooh, I'm not so sure if I like this new setup. Oh, you know what I just realized? I misinterpreted the graph. It's not 0, it's 1. Sorry about that. 1, okay, now that I see it, now I wasn't looking carefully enough. I assumed that was 0. That means there's no value of X that could cause this ratio to be equal to 1. In other words, the numerator and the denominator are never going to equal each other, no matter what the value of X is. And that's why this is happening. Okay, now we got that straight. Okay, now how about this one? Well, this is very closely related to the square root of X. It's the square root of X minus 3. And what happens is all you're doing is basically shifting the function over to the right so that it starts at 3. Okay, so in other words, so that means that the 3 is the smallest value that we can plug into this formula. So the domain is everything from 3 up to infinity, including infinity. If you notice, the range is all positive values. Okay, it can be 0. If we plug in a 3 in here, we'll get a 0. And if X is even anything above that, we'll get a positive number. What we're disallowing for is negatives. All right, now what's coming up here is an overview of the domains and ranges for all these different cases that we've been looking at. So for example, the constant function y equals c, or f of x equals c. You can see that it covers the entire real number line. The x's can be anything, but the range is just that one value. Now, sometimes you see this notation. I mean, we could have just put a c here, I guess, but this is an interval that indicates it's simply the value c. Right? It looks a little strange, but that's perfectly valid notation for indicating it's a constant. All right, what else do we look at? The identity function, remember, this is just a straight line through the origin. Because oh boy. Let me see if I can draw that again. Yes, you can see it cuts through the origin and it has a slope of 1. There's no value of x that could lead to any kind of problems like division by 0. And y can be anything as well. Absolute value. All right, we went over this yesterday. What's interesting about the absolute value function is that x can be anything. It can be negative, it can be positive, it doesn't matter. So the domain is everything from negative to positive infinity. The range, as you notice, must be positive. Okay? Or actually, I should say non-negative. Because it can be 0. Okay. The quadratic function. Now, this is the one we discussed this very briefly a few minutes ago. The domain is just all the real numbers. The range depends on the starting point for this parabola. Now, we'll see later on, although you may have encountered this term yourselves in a different class. For any parabola, there's going to be a single unique point at which it reaches either a maximum or a minimum value. Okay, this parabola facing up has a minimum value. And this one has a maximum. Those 2 points are, each one is referred to as a vertex. In this context, the vertex is either the maximum or minimum value of a parabola. Actually, let me write it a little differently. The vertex is actually not a single value, it's a point. Let me call it maximum or minimum point on a parabola. That's better. Because it could go either way. And of course, remember, this is the one where a is positive. This is the one where a is negative. But the range can include that a point. Not a, the minimum or maximum. So this is one where there's 2 possibilities. And by the way, it's often the case with the vertex that we indicate it with the values h comma k. I do not know why those 2 were chosen. But that's the standard practice in math. H comma k is used to represent the x and y coordinates for the vertex of any function. It doesn't just have to be a parabola. And so the k represents either the minimum or maximum value in the range. So for this one, the range is everything from k up to infinity, including the k. For this one, we go from negative infinity up to k, including the k. So in other words, the range depends on whether the parabola is facing up or down. And remember, a comes from the definition of a quadratic equation. Okay, so that's that. Okay, here we go. Now for this one, well, all right, I'll tell you what. Let me show you where this came from. It says right here, the vertex is negative 1, 0. Let's say it looks like this. Here's our function. In fact, let's go to Symbol Lab and take a look at it. Actually, the Symbolab, I think, can figure out the vertex for us, but let me just show you how it was done. Two x squared plus 2x plus 1. Oh, it does touch. What do you know? Negative 1, 0. Okay, I did not draw it well then. How interesting is that? Actually, we could have figured that out with the quadratic formula if we really wanted to. But negative, oh yeah, it does say that there. Okay. But here's the thing, where did we get that from? Well, remember, quadratic equation is written as ax squared plus bx plus c. The vertex, the way it's written, h equals negative b over 2a. K is simply f of h. So in this case, h is b is 2, a is 1, and c is 1. Negative b over 2a would be negative 2 over 2 times 1. So that's the x coordinate. F of negative 1 would be negative 1 squared plus 2 times negative 1 plus 1, 1 minus 2 plus 1, which is 0. Okay, so that's where that came from. So actually, the whole point of all this was to discover the range. Okay, so in other words, this is as small as the function can get, 0. It can get bigger, but it can't get smaller. All right, very good. Oh, I forgot to check. I know it's here. Now, the great thing about the Symbolab is if you can't find what you're looking for, you can go to Google. It's usually easier. I find it to be easier. Um, oh man, I don't know what all that is. Okay, but I know it can do that. In fact, I'll tell you what. Let me go to Google. Oh no, maybe it would. I could do that here. All right. Okay, so let's see if we can do this one. X squared plus 2x plus 1. Oh yeah, there it is. Yeah, because remember, the vertex is either the minimum or maximum of the function. And since this function faces up, this must be the minimum. So it doesn't actually, it just says the minimum, but it means that's what the vertex means. Okay. Okay. Oh, and here's another example of this. All right. So let's do this, work this through. Now, this one is clearly facing down. Let's say it looks like this. I'm not sure, but let's just say that's what it looks like. So based on the formula I showed you before, h will be minus 2 over 2 times negative 1. And then k is f of 1, negative 1 squared, is 2 times 1 plus 1. 1 plus 2 plus 1. Oh, I think I've done something wrong here. Let's try that again. F of 1 is negative 1. So, okay, that's where I screwed it up. Okay, no, the negative has to be there. I accidentally squared the whole thing. That's where I messed it up. Okay, very good. It's negative 1 plus 2 plus 1. Yeah, it's 2. All right, so that's definitely 1 comma 2. That is our vertex. That means the range would be everything from 1 down to negative infinity. And there it is. Okay, very good. Oh, and that's what it really looks like. Okay. Oh, geez, look what I did. It's sorry, it's the 2 that we're looking for, not the 1. For the range, it's the y coordinate. I copied the wrong one. It's negative infinity up to 2. All right, that's better. Much better. All right, let's look at some of these others. Now, we already discussed this one, the cubic function. Pretty much, they don't all look exactly the same, but the bottom line is there's no issue here with taking cube roots of negative numbers, or cubes, I should say. So the domain and the range are both all the real numbers. The reciprocal function, we've seen this before. We have 2 asymptotes, the horizontal and vertical axes. So therefore, the domain is everything except 0. The range is everything except 0. All right, and then I think there's one more here, 1 over x squared. And again, we've been talking about this. This time, we're only restricted to the first and second quadrants. So what we're seeing here is that the x cannot be 0, because that would lead to division by 0. So the domain looks like this. The range, on the other hand, has to be strictly positive. And you notice the distinction between non-negative and strictly positive. Strictly positive leaves out the possibility of 0, whereas non-negative includes a 0. Okay. Oh, there's a couple more. Square root function. And as we discussed before, we can have zeros, but we cannot have negatives. So both of these are non-negatives, meaning we can include 0. And finally, the cube root function. It's something like that. Oh, maybe that's not. Let me go back here and get some help from Symbol Lab. Actually, let me do it this way. It has a cube, I mean, a root function. See, and it's telling us the domain and range are both all real numbers. Actually, sometimes it offers to show you why. Okay, so my graph is a little, no, I see what I did wrong. All right, let's try that again. That was actually x cubed that I just drew up. I drew my mistake. Okay, now here's a tricky one. What are the domain and range of 5 over x plus 2? Well, right off the bat, we can see that x cannot be negative 2. So the range. Now, again, this is going to be tricky. We don't have the techniques yet to prove why, but let me just show you the graph. And you can see, although looks like that's negative 2. Yeah, that's the value you can't have. So only negative 2 is disallowed. Oh, I'm sorry, I'm looking at the wrong. No, it is 0. I was right the first time. The vertical axis is for the range. That's cutting through and let's say this is negative 2 is the value of x that we can't have. No, I had it right the first time. Sorry. It's the range though that can't be 0. That's 0 right there. So and again, whenever you've got a constant like that in the numerator and x in the denominator, even though it's a function of x, you can rule out right away the function ever being equal to 0. There might be others, but in this case, it's just the 0. Okay. So that's that one. Now I mentioned this the other day. The absolute value function has 2 distinct regions to it. Their properties are different from each other. All the other functions we've seen are what we say smooth and continuous. This one is not. The fact that there's like this sharp point at the bottom is an indication that this is not smooth and continuous. We just find this as piecewise. It's almost like there's 2 different functions here glued together. And you'll see later on why this can cause problems. But the idea here is that you've got to have a separate definition for each section or region of this function. So I showed it to you the other day. As long as we are in the first quadrant, the absolute value of x is simply equal to x. Otherwise, we have to get rid of the negative sign by multiplying it by -1. So this is the notation we use for piecewise functions. In other words, it's showing us the 2 distinct regions of the graph. And there can be more than 2, by the way. It can get very strange in a hurry. Well, you don't run into that very often, but 2 is not that unusual. There's 2 regions, complete distinct regions of this function which have very different properties. Now, here's another example. And now this one, it won't be obvious right away what it looks like. In the first quadrant, the function is x squared. Okay. In other words, to the right of the horizontal axis. Here, though, the rest of it is 3x. So you got 2 things going on here. You've got a quadratic function and you've got a straight line. So it should look something like this. You can see there's something strange going on here because the slope changes dramatically at this point. And that is often a sign of a piecewise function. A very sharp break in the slope is an indication that it's a piecewise function. Now, by the way, Symbolab is capable of graphing this thing. It's just that I keep forgetting how to do it. I know it's here, but I'm going to go to Google and find it. See how nicely it's set up. So in other words, I'm going to tell it it's x squared, where x greater than or equal to 0, 3x everywhere else. Yeah, in fact, they're even trying to show you what it would have looked like if it was all the same function. So you get this curve, and you've got a straight line. This is what it looks like. It's very strange. Okay. Rates of change. Now, this is something that will prove to be incredibly important as we go forward, especially, well, I mean, any aspect, part of one of the motivations for creating calculus in the first place was so that Newton could help explain the laws of physics that he was inventing. And rates of change are an incredibly important concept in calculus. In fact, soon enough, we'll be defining one of the most important concepts in the whole course in terms of rates of change. It's not that unusual to try to understand or figure out how much one variable is changing when there's a given change in another variable. In other words, how much does one variable affect the other? Just as a quick example, what if a company wants to know if we increase our advertising budget by $1 million, what will happen to our sales next year? That's a classic example of what we're about to do here. So we're going to define this as the change in the output. Now, this actually can be written as delta y over delta x. So using the example I had a minute ago, x could be advertising dollars, expenditures. And y could be sales. So if, let's say, I add $1 million to my budget and my sales go up by 2 million, that means the rate of change is $2 worth of sales rather are the result of each extra dollar of advertising. And if that's the case, I certainly want to advertise as much as I can. That's a pretty good rate of return. Every dollar of advertising gives me twice as much back in profits, or sales rather. I like that. Formally, we're going to define it like this. Okay, so we're assuming that there's 2 points on some function, which does not have to be a straight line. Oh, sorry, what did I do? So you recognize this is just the slope of a line, although the function that we're analyzing here, like I said, doesn't have to be a line. This applies to all functions. It's the change in the dependent variable, which results from a given change in the independent variable. We can write that as y2 minus y1 over x2 minus x1, or the y's can be replaced with f of x. And that's all there is to it. All right, now here's a very simple example of this, and this is a linear function we're about to see. Suppose we're told that gas sells for Let's just make up a little chart here. By the way, there's an implicit assumption here that x is the year is the x variable and the y is the price in this case, because the price depends on what year we're in. It's not the other way around. So in 2009, we were paying $3.29. Now in 2019, and it's up to $3.49. What was the average rate of change over that interval? So we can think of this as x1, x2, y1, and y2. Okay, now, of course, here's the thing. If you didn't recognize that the years are the x's and the y's are the prices, you're going to get this backwards. So we'll try to make sure that in these cases, it's obvious which is the x and which is the y. Okay, so let's jump ahead and plug these into our formula. So in other words, the price went up 20 cents over 10 years, which means obviously on average, it's 2 cents per year. So this is a very simple case, but I mean, we could have done it in our heads, but it gets much more complicated when the function is not linear. Okay, like if we're moving from one point to another point on a parabola, let's say. But the function, the equation always works. Now, here we go. There's some interesting data. We have years. Now, if you're not familiar, S&P 500 stands for Standard and Poor's. What it is an index that represents the average price of the 500 largest stocks in the United States. It's very commonly heavily watched on Wall Street because it's a good indication of how the market is doing, which in turn is a good indication of how the economy is doing. So when things are going well, when we hear good news, the Standard & Poor's tends to go up. When things are going badly, like we discovered that inflation is higher than we expected, the S&P tends to fall. Okay, so a lot of attention is paid to this in the markets. So here we have a function. Now this function, we don't know what it is. You know, a lot of times we assume we have some function that describes the relationship between x and y, but here all we have is a bunch of observations. So we can't, you know, there isn't any graph that we can draw for this. All we can do is take the data that we have. So what we're looking for is the average change over these 5 years, or 4 years rather. And once again, these would be the x's, these would be the y's. So for example, this is x1, x2, x3, 4, and 5. So the average rate of change is going to be oh, sorry, not x2, x5. Okay, so we're going to do that on the next slide. Oh, I didn't, you know what? I didn't even realize it. I assumed that it was going to ask us about the change between 2015 and 19. No, it's only asking for 16. That means that this is actually Y3, by the way. If you start with X, oh boy, well, that's awkward. So we're going to just think of 2016 as year 1. And 2019 is year 3. Okay, so that means that this is actually Y3 and Y1, X3 and X1. Either way, the market went up 763.86 in 3 years. So therefore, the average gain was about 254 0.62 points. Okay, so that, I mean, this is a classic example of how this works. On average, the index went up $254.62 per year. Now, here's an example of what I was alluding to earlier. This is clearly a quadratic function. And let's just go to Symbolab and see what it looks like. X squared minus 3x and the graph is okay. So in other words, what we're looking for is the points where x is 3 and x is 6. Now, I don't think, okay, well, that's what it looks like. So we're looking for basically like here and here, let's say. Okay, let me just clean this up a bit. I'm still getting used to this tablet. It's not exactly the same thing as writing on the whiteboard, that's for sure. All right, 3 and 6. Now, obviously, we're going to have to evaluate this function at those 2 points. We need to know f of 3. This is our y value. 3 squared minus 3 times 3 plus 5 is 9 minus 9 plus 5, which is 5. And then for 6, $36 minus 18 plus 5, that would give me 23. So you can think of this as the ordered pair, 3, 5, and 6, 23. And then what we're aiming for is the differences between the y's divided by the differences in the x's. Okay. So in other words, this is y2. And that gives us 6. So on average, between those 2 points, the rate of change is 6. Or you can think of it as saying that the slope between these 2 points is approximately equal to 6. And you can draw a straight line here. Now, if you notice, the straight line doesn't exactly match up with the function. Okay, and what we're effectively doing is averaging out the slopes at all these different points along the curve. But right now, between these 2 points, the slope of that straight line is 6. Okay. So, determining the changes in a function. And this can often be very important. Let's say we have something like this. Now you can see this function goes through some phases. It goes up and hits a maximum here. It turns down again. This is a minimum here, and then it goes up forever after that. Now we're going to spend a lot of time with this type of thing in Calc 1, identifying the points where the function reaches a maximum and a minimum value, and where it changes. In other words, you see how the slope is going from positive to negative back to positive. The slope at these 2 points is exactly 0. In other words, if I drew a tangent to the function here, the slope is the tangent line is flat, which means the slope is 0. So we'd like to be able to know where these points are. Now, I just want to mention some terminology here, because this is the largest point within this area of the graph. This is sometimes called a local or relative maximum. Down here, this one would be the same reasoning, a local or relative minimum. Now, we also have the concept of a global or absolute minimum or maximum equals the smallest or largest value for the whole graph, that is. Whereas these are only true within a narrow area. In other words, the one on the left is the largest point within that area of the curve. But we can clearly see that over here, the function does rise above that point. And then down here, this is the local. This is not the smallest point in the entire graph, but it's in that neighborhood, we call it. It is the smallest. I'm trying to think of an analogy. It would be like, I guess, imagine that a corporation has like their headquarters somewhere, but they also have regional offices. I'm really drawing a blank here for an analogy. So in other words, these are offices of the corporation, but they're not the biggest. It's not the main office. But anyway, all right, well, I'll think of a better analogy later on. So, but anyway, yes, we can run into this. So you can see this is kind of like a roller coaster ride. It goes up and it starts to go down and then back up again. And once it goes up again, it'll never come back down again. Now, there's different ways we can identify these points. And these are collectively known as relative extreme. Now we have to be careful here sometimes with our these terms that we're using, because a lot of it is based on Latin. I just want to quickly throw this in here, a little bit of a Latin lesson. The plural of maximum is maxima. The plural of minimum is minima. An extremum is either a maximum or a minimum. The plural of extremum is, as you can guess, extrema. Okay, just want to get that out there so we don't have to keep mentioning it over and over again. Remember, we're dealing with Latin here, and so sometimes the way we turn them into plurals is a little different than what we're used to seeing. Okay. And so relative extrema means it's either relative maximum or relative minimum. Now, what is important to note is that to the left of that maximum, so the function, actually, let me draw a new graph so it doesn't get too cluttered. The way you know is that everywhere up to this point, the slope is positive. Here the slope is exactly 0. Here the slope is negative. Slope is 0 again. And here, of course, the slope is positive. So you can basically tell where the extrema are by looking at the slopes of the function on either side of that point. Now we're going to see later on a more sophisticated way of doing this. But for now, it's enough to note that the extrema are characterized by the idea that the slope is 0 at exactly that point, and on either side of it, the slope is changing sign. Okay, and this can happen many different times. This function, by the way, is probably a cubic function. You can tell because it cuts through the axis 3 times. I don't know. Oh, actually, yes, it is here. X cubed minus 12x. So that's kind of one of the characteristics. It has a unique curvature to it, and it can go through the axis up to 3 times. Okay, a parabola obviously can't do that. It's limited to 2. All right. Let's see. Where are we? Oh, and you can find those points. By looking at the graph, you can see that the maximum occurs when x is -2. At that point, y is 16. So this is our local maximum. And Symbolab will show that to us as well, if you ask for it. On the other side of the fence, at 2, we have the local maximum, and that indicates that this is our local minimum, rather. Actually, let's do that. Let's go into Symbolab for a minute and see what it looks like. If it doesn't explicitly tell us, you can ask for it. It used to, with the old setup, automatically give you all that information. Now, I guess you just have to look for it. I mean, it looks prettier, I have to admit that, but I don't think it's as user-friendly. Okay, well, hovering it is helping. The maximum is -216. Minimum is 2 -16. You know what, I'm starting to think maybe all you have to do, as long as it's in italics, I guess that counts. Oh, there it is. Huh. This symbol. I'm still learning it. Okay, so let's see, where are we? Okay, this is a completely different topic. So as we did yesterday, I think we'll stop here because we've been going for about an hour. This will be part 2. And then maybe tonight, maybe tomorrow, I'll post part 3. We don't want to get too overwhelmed in the first week, but yeah, by the time the week is over, we will have seen all of the material that we need. Basically, I'm not sure how far we need to get, but I'm trying to align it with the normal spring and fall semesters. But right now, we'll just keep going at this pace, I think, and we'll be done in plenty of time. So I'll just stop it right here, and then the next video we'll pick it up right here with composite functions, and then we'll take it from there. All right, so I will see you all next time.